I go. Start. Okay, so first of all, let me thank the organizer for inviting me here. It's a pleasure to stay here. So today, or actually this week, I will talk about a recent work that I did with Massimiliano Berti, Paolo Ventura, and also, if we have time, with Livia Corsi. About the instability of stock swap. Okay, so my story begins in 1967, and the protagonists of the story are stock swap. So stock swap are traveling one-dimensional, two-periodic solutions of the water waves equation. So they have the form of a fixed profile in space, periodic in space, which travel at constant speed. And so I'm sure that so this is the picture that you need to have in mind. So you see that these waves are essentially one-dimensional in the sense they are constant along this direction. So they depend only on the direction of propagation of the wave. They travel at constant speed. And also you see that here the patterns repeat, and so you see that the distance between the two crests is obviously 2 pi. Okay, and it was widely believed in the 60s that stock swap were stable solution of the water waves equations, and so there were people around the world trying to prove both experimentally and analytically that stock swap that you can observe in the sea are actually are stable solutions. And so the story that I've been told is this. So there was a student in Cambridge named Fair, which went to do this thesis with Benjamin, who at the time was a professor at Cambridge. And Benjamin gave him, as a PhD thesis, to prove experimentally the stability of stock swap. And so the experiment was supposed to work in this way. So they had a very long tank. And on one side of the tank, they had a wave maker producing a stock swap that you can see here. And then they needed to, so that the stock swap started traveling along this tank. And the goal was to obtain stock swap on the other side of the tank. So very, very far away. And the experiment kept failing. And of course, Benjamin did the only thing that an advisor can do. So he kept telling Benjamin Fair to try harder to improve the experiment. And they try, and then they recheck everything many times. Till at some point, they realized that it was not a problem of the setup. It was not a problem of the experimental, but the fact that is that stock swap were actually unstable solutions of the water wave systems. And so in their world, it was found that the wave train may develop conspicuous irregularities if it travels far enough, even when departure from periodicity can hardly be detected near the origin. Eventually, at great distance from the origin, the train may become completely disintegrating and the energy redistributed over a broad spectrum. And nowadays, this phenomenon is known as Benjamin Fair or modulational instability. And it is the heuristic mechanism that under long wave perturbations, stock swap become unstable. And after the experiment, or more or less at the same time of the experiment of Benjamin Fair, it was realized that this phenomenon is ubiquitous in many other areas of physics. And then there has been a huge literature to try to understand this phenomenon. Okay, from a mathematical point of view, the question is more or less clear. So stock swap are solutions of the water wave system. So you take the Stokes wave solution, you plug it in the water waves equation, and at first order, so the first approximation, you get an equation dTV equal the linearized operator apply to the perturbation. So this is the linearized operator. I will write it down probably tomorrow explicitly, plus a quadratic correction. And so, well, you do, so the first question, the first natural question is, if you want to understand the stability of the Stokes wave, you need to understand the spectrum of the linearized operator. And so the mathematical question is, what is the spectrum on L2R of the linearized water waves operator at a small amplitude Stokes wave? And then the modulational instability, so the Benjamin Fair instability in mathematical terms, is the phenomenon that the spectrum of this operator has non-trivial branches as non-trivial branch with real part of the spectrum strictly positive. A couple of remarks. So the phenomenon is essentially due to the size of the domain. So this is also true not just on R, but on a very large box, 0 L, with L very large. And so it is represented in so it applies also to the tank experiment of Benjamin Fair. And as I mentioned, the pioneering works was done by Benjamin and Fair, by Lytle, by Wheaton, Zakharov, and they detected an instability also with some heuristic computation. They detected an instability near the origin of the complex plane of the spectrum. And then in the 80s, McLean numerically detected also a new type of instability in the spectrum, which is away from the origin. And then there's been, in the last years, a lot of activity for dispersive PDEs, for example, NLS, generalized KDV, Wheaton, by many people, where they also, so for all these kind of equations, you can quite easily construct traveling wave solutions, and then you ask whether these solutions are stable or unstable, and in general, the answer is that they are unstable when considered on large domains. And instead, when you are on a fixed domain, you get, in general, so the folklore is that on a 2π domain, at a small amplitude wave, traveling waves on 2π domain in general are stable. Okay, so what is the spectrum of this operator? So let me tell you. So the easiest things is you use numerical methods to draw the spectrum. And so the first numerical result, rigorous numerical result, was done by De Koning and Oliveras, and they plotted this figure. So this is the linearized operator at a small amplitude Stokes wave, the spectrum of the linearized operator at a small amplitude Stokes wave. And so you think to ping, you see that there are branches of spectrum with real parts strictly positive, and they come into different forms. So the first is near the origin. They seems to make a figure 8. Yeah. And then what they see, actually, first was done by McLean, and then also more recently by Cridon, De Koning, and Trichenko. They see island along the imaginary axis, shrinking in size, and in principle going all along the way.
What's the difference between
the difference between this Cridon, De Koning, Trichenko?
No. In the figure on the right.
Yes.
Figure 8 is plotted P.
Ah, no, just follow. There is no.
But usually, because sometimes it's good, very bad.
No. This is just, I don't know. No. Okay. This is just color. Different shape. Okay. And okay, so this is what you see numerically. And then what about analytical result? So the first rigorous analytical result was done by Bridge and Milke for the water waves in finite depth. And the result so brings a mean and finite depth. So if the depth is sufficiently larger than this critical threshold, and then even more recently by Nguyen Strauss for the infinite depth case. So what they were able to see and to justify is that the spectrum makes a small cross here. So they justify the cross, amidate. And then together with Massimiliano Berti and Paolo Ventura, we were able to describe the complete figure eight. And then Ure Yang in finite depth, and then together also with Massimiliano Berti and Paolo Ventura in deep water, we describe analytically the first isola. And then there has been also in the recent years a lot of activity for the same problem, but for 3D water waves. So Stokes waves are one-dimensional solution, but of course they are solution of the 3D water waves equation. So you can ask yourself the same question for the 3D water waves equations, and then to study also this stability or instability along transversal perturbation. And so we mentioned some recent work by Cridon, Nguyen, Strauss, and Changzhen, Zvetkov, and so to say Zvetkov and to say Changzhen are for actually for instability of regard the stability and instability of solitary wave solution, and instead for Stokes wave solution there is this work by Cridon, Nguyen, Strauss, and the conjecture is that there exist infinitely many isolas in the spectrum centered along the imaginary axis and shrinking exponentially fast away from the origin. Okay, so let me give you two take-home theorems. So the first one is, as I mentioned, with a result of Massimiliano Berti in SISA and Paolo Ventura, who now is a postdoc in Milan, but he was a PhD student at SISA. And so we give a complete description of the spectrum near zero of the linearized water waves equation on R at small amplitude Stokes wave, both in finite and deep water. So we were able to completely justify and describe the figure eight instability. And then more recently, together with Livia Corsi, we have the other result. So you give me an arbitrary P as large as you want. And then provided the depth, so this result is infinite depth, provided the depth of the water is outside a closed set of isolated points, then the spectrum has P disjoint isolants in the upper half plane away from the origin. So you give me a P, and we are able to find P isolants. So going up in the original plane and shrinking exponentially faster. So the size of the P isola is epsilon to the P. So after even not too large P, they become numerically undetectable, but they exist. And of course, there are also P isolas, P symmetric isolas going down the imaginary axis. And let me also mention that the method that we developed here is very flexible. And recently with Antonio Radakovic, we were able to prove the figure eight instability spectrum for generalized KdV equation. And so figure eight appears essentially universally in all the model similar to Corto-Vertebrese. And then together with Roberta Bianchini, Stefano Pasquali, hopefully soon, we use also this method to prove linear instability of internal waves in the Boussinesq equation. So Boussinesq equation also has traveling wave solution, you linearized, and then you wonder what is the spectrum of Boussinesq equation at an internal wave, and with this method we can prove that there exists isolants. Okay, so the goal of this week is so to prove the figure eight, at least, and then we see how far we go. Okay.
So that's a second theorem that follow the theorem you mentioned.
No, because the result with And also, I will do also something very classical, which is to construct Fourier Stokes wave, which is done by. So it's a nice, it's a beautiful application of importation random heuristic. It can be done quite easily. Okay. So let me start. Let me start the water with equations. Okay. So the water equation, so you take a fluid which is incompressible and irrotational under the effect of the gravity. And which occupies at time t, it occupies a domain with infinite depth. So let me make a picture. So this is the C, and then this is the profile of the wave. So the serial profile of the wave will be denoted by theta and x. And here there is the water. And I am in the situation, so there are in general, there are many situations to consider. So we consider a fluid in infinite depth. So here there is no bottom. And so this want to somehow describes the waves in water. So when you are in the middle of the ocean, so the depth of the wave is much larger compared to the profile, the wavelength of the file. There is another interesting situation in which you put a bottom, a flat bottom here at that h. And of course, there are all the variations, but you can consider also varying the bottom, but I will speak on the water. And so eta is the free surface, the profile of the wave. And then the fluid occupies the domain, so we'll denote by the eta, the domain. So this is the set of x, y in R times R, such that y is smaller than eta in S. And so for this week, we concentrate on 2D water waves, meaning that all the waves are constant along the direction which enters in the network. Okay, because we want somehow to model model the situation of the Stokes wave in which the Stokes wave is constant along this direction. Okay, so the equation of motions are the Euler equation. Equation of motions are the Euler equation for the velocity field plus boundary conditions. So we have the velocity field u, which are the here u, which depends on x, y, and t, and it has two components, the horizontal component, y, t, v, x, y, t is the velocity field. And so the fluid is incompressible, meaning that the divergence of u is equal to 0. The fluid is irrotational, meaning that rho u is equal to 0. And the fluid obeys the Euler equation, meaning that du plus u over gradient u plus the gradient of the pressure is equal to minus g e y. So that is the action of the gravity is falling down with the gravity, and dy is of course the vector of the one. So these are the equation of motions, and then we have three boundary conditions. So the first boundary condition is the kinematic boundary condition. Kinematic boundary condition, which tells that the free surface moves the fluid. So essentially tells that if you have the particles which at time 0 is on the free surface, then it will stay on the free surface for all time. and it reads the following. So theta T is equal to the square root of 1 plus dx squared, and then we have the velocity, scalar product, the normal. So this equation after the surface, it's equal to theta x, and theta is the normal. N is the normal, sorry, n is the normal at the surface. So this is n. And so how does n looks like? So n, so you see the fluid, the free surface is parameterized by the curve x theta px, and so the normal at the free surface is the vector minus theta x 1 normalized. So this dynamic boundary condition, then there is another condition, and the other condition is the so-called the dynamic condition, the dynamic boundary condition, which tells that the pressure of the fluid, so P, coincides with the atmospheric pressure at the free surface. And then the third condition is the condition at the bottom of the domain, which tells that at the bottom, or as you go down in the depth, so the fluid is essentially horizontal. So the velocity field, as you go down depth, it has more and more only the horizontal component. So the second component of the fluid is zero. And that means as the limit when y tends to minus infinity of the second component, I denote d dxy is equal to 0. Okay, so these are the equation of motions, and this is the first and last time that you will see this equation during this week. Now I switch to another formulation, which is more convenient for what we need to do. And then the formulation starts with this observation. So the other condition that you have, okay, let's start from this. So rho u is equal to 0, meaning that there exists a velocity potential. So which I denote by phi, which is the velocity potential, But the u is the gradient of phi. Okay? Then what are the equations for phi, for the velocity potential? So the divergence of u equals 0, meaning that if I take the divergence here, the divergence of the gradient is the Laplacian. So Laplacian phi equal to 0 in the domain. Then what we have this. So p, what is p is the second component of u, and u is the gradient of phi, meaning that b is the derivative with respect to y, the second component of phi, and this tends to 0 as y tends to minus infinity. So this is the bottom boundary condition. And then with a little bit of work, you can also transform, you can also write the Euler equation in terms of the velocity potential. So u is the gradient. So in this formula, you write u equal gradient of phi, and you do a little bit of algebra, and you find the Bernoulli equation of the velocity potential. So dt phi plus 1/2 gradient of phi square plus the pressure plus gy equal to 0 in so these are the is nothing that the Bernoulli equation of the equation for phi. Excellent. Okay, so if you know u, if you know the velocity field, then you know the equations. Of course, you know everything about the velocity potential. But now let me do this. So we define Let me define this. So define psi x as phi of t x eta dx. So this is the trace at the free surface of the velocity potential. Okay, so if I define this now, what are the equations fulfilled by phi? So for phi, I have Laplacian phi equal to 0, Laplacian phi equal to 0 into y. Let me draw again the picture. So Laplacian phi is dy. So Laplacian phi equal to dy. And then you have that phi now is equal to psi at the surface, so at y equal eta to x. So we have this boundary condition. And then we have another boundary condition at the bottom, dy phi. Dy phi tends to 0 as y tends to minus infinity. And so we have a Neumann condition at minus infinity. And so you recognize that this is an elliptic problem. With Dirichlet-Neumann boundary condition. That you can solve. Okay, so there are more or less standard methods to solve this. The eta. Okay, so far so good, but now let me make an observation. And the observation is so if you know u, you know phi, and if you know phi, you know psi, and so if you know eta and u, you know everything in this problem. But now, what happens is instead I give you eta and psi. So if I give you eta and psi, so if you know, so the observation. If I give you eta and psi, well, you take eta psi, you solve the elliptic problem, you find the velocity potential, you take the gradient of the velocity potential, you have u, so you have everything. Meaning that the original problem, so what is written here on the blackboard, can be formulated only as an equation in terms of eta and psi. And this was done by Zakharov. This is Zakharov of observation. It was done by Zakharov. And he wrote the waterways equation just as an equation in terms of eta and psi, and these are just data. So the advantage is that these are data on the surface. These are just data on the surface. Okay, and now I'm going to write down the equations in terms of eta and psi, but before I need to introduce an object, and the object is the Dirichlet-Neumann operator. Dirichlet-Neumann operator. Dirichlet-Neumann operator, which I denote by G eta psi. And so, well, this is the operator that maps so this problem, it maps the Dirichlet datum psi into the Neumann datum. So the Neumann datum is the derivative with respect to the normal. So this maps the datum into the normal datum, and so it is defined explicitly this way. So G eta psi is square root of 1 plus eta x squared, which is just the norm of the normal, and the derivative with respect to the normal of the velocity potential. So this is the Neumann datum evaluated at the free surface. y equal eta x. And so recall that the normal derivative with respect to the normal is, of course, the normal times the gradient. And so if I use the expression of the normal, which is written there, what I get is first I get the component. So this is the derivative of y of phi evaluated at dx eta dx minus eta x dx derivative respect to x of the velocity potential dx eta dx. So question for you. How does this operator depends on psi? And how is it dependent on psi? Question for the student, not for... Yes.
Inside to solve it.
Of course. And so how is the dependence of this operator on psi? The notation suggested. So the question is, how does the solution of this problem depends on the boundary condition?
If I'm going to delete that, it should be 0.5 psi 1 eta dx.
This because you evaluate this function at the profile. So here, but then if I give you the Dirichlet data at this boundary, the elliptic problem, the solution is linear, depends linearly on the data. And so the maps that psi it associate g eta psi is linear, and instead the maps so as a function of eta, is very complicated. It is highly nonlinear, but it is analytic, and then I will specify from which space to which space in a few moments. Okay. So for a moment, let me keep writing formally the equation. So how does the equation of motions, which are still written here, looks like in this coordinate? So the first one is very easy.
So sorry, just on this. So there's no way to put it more explicit.
There is no
way to put it more explicit.
Then this. No.
Okay. That's
No. What you can do is so this operator, this is analytic operator, so you can compute Taylor expansion.
okay.
And these are explicit, and you can do them. Very explicit. I cannot hear you.
I mean, it depends on the but in the well.
But in any case, in order to compute it, you need to pass through this.
Yeah,
I don't know. Not explicit in the sense that if I give you eta, so either you compute the jets of the Dirichlet operator, and these are explicit. So the first one that will show you actually of eta, the modulus of d, and then so this is the first correction, and then you have minus dx composed eta composed dx minus modulus of d composed eta composed modulus of d plus terms which are quadratic infinite, and this you can write at any order.
Then write it as an answer operator from what you have one way you need to
Yes.
Operator, which may or may not affect the plot
Good question for you would be what would be the best way for a computer so to put in a computer the integral formulation, because with the integral formulation you can compute the standard. Okay. Also, at least if the Stokes wave is small, this becomes smaller and smaller. Okay, so in this equation, so this seems sorry, it seems weird that we have introduced this equation, but look at this operator. Look at this operator, and look at the kinematic boundary condition. And remember that Q is equal to the gradient of phi, and they are the same equations. So meaning that in terms of the Grisham-Neumann operator, the kinematic boundary conditions become dp eta equal G of eta psi. That is the first equation. And then it is a little bit more work, which maybe is not worth too explicitly, but you can also write the Bernoulli equation. So the Bernoulli equation is phi, so you evaluate at the free surface. You evaluate the Bernoulli equation at the free surface, and you use the fact that at the free surface you have this identity, and you play a little bit with the derivatives. It is not immediate, but it can be done. And what you can prove is that you can derive an equation for psi, and the equation for psi is dt psi equal minus G eta minus 1/2 Cx squared plus 1/2 G of eta psi plus eta x Cx squared over 1 plus eta x squared. And so these are the water waves equations in Zakharov. The Zakharov formulation, Zakharov formulation of the water waves. Okay, so what is the advantage of this formulation? So for me, the advantage is this. So the original problem, so one of the difficulty of the original problem is that it is a free boundary problem, in the sense that the boundary is not given. The boundary is eta Tx, which is an unknown. It is the profile. It is the profile of the wave, eta Tx. So it's something that I want to know. So the profile of the wave is not given. It evolves with time. And so this is a free boundary problem, and instead this system of equation is not anymore a free boundary problem. So this is a system on. So in our case, here the variable will stay on RB, or actually on R for the quadratic, or in our specific case, even on the torus, because we are interested today we are interested in constructing Stokes wave, which are 2 pi periodic. So this is not anymore a free boundary problem. It depends just on the data on the surface. So not anymore the boundary. But the disadvantage, well, one is that the disadvantage that it depends on the Grisham-Neumann, which is a complicated operator. So you need to understand the Grisham-Neumann. You need to understand the Grisham-Neumann operator, and it is a quasi-linear system of equations. It's quasi-linear. Meaning that the nonlinearity, for example, here contains the derivative of the highest order. And this makes the problem difficult for us.
Sorry, but what about the condition of P? You cross the information.
Yes, you don't need anymore. So you reduce the equation, you reduce the water waves as an equation on the surface. And you don't have any more boundary constraints. This is another advantage for me.
But the question, put out the relation of the Grisham-Neumann operator.
you are using phi.
Of course.
So
It is
phi-
hidden.
in phi is included with it. So
It is hidden.
it's there.
Inside
The
here.
condition is not disappearing. It's just
Not completely.
incorporated by the declaration.
It is incorporated with normal. Sure. It is hidden inside this operator because if you want to compute this operator, you need to solve the elliptic problem. And so it is there. But in principle, for many things, you will need only some analytical properties of the phenomenon. You do not need, for example, you do not need the explicit formula. For example, you will need just that the phenomenon operator has a certain regularity, it depends analytically on internal variable, it loses a certain number of derivatives, and so on. You have a Taylor expansion on the phenomenon operator, and so somehow, in many cases, you can hide the boundary condition very well.
Yeah.
But it's there. It's there.
In a naive point of view, very naive, because you could start an iteration where in a step you solve that, in a step you go there. But this is possible. Now, so necessary if you use this.
Yes.
Because if you want to do that outside the analytic framework, maybe you will need some analytic steps.
No, but the analyticity is the dependence of the operator on eta, not the regularity of the way. So this is
I'm not talking about regularity. I'm talking the fact that you can expand the operator as much as you want in terms of eta.
yes.
So it allows you to have at least at the lower order over the terms that you like.
Yes. Exactly. Okay, these are expansions which were first computed by Walter Gray.
Having this expansion is not making explicitly the sense about the set, but somehow it is a way that you can work algebraically.
Exactly.
The question is that if you want to keep the Tillich-Neumann operator highly nonlinear as it is, forgetting this dependence, then maybe I don't know if some of the try the one has to solve separately that the problem, and then what was the iteration scheme between these. It's a kind of issue. I don't know if somebody will have it.
Cioè, to construct an iterative scheme to do what? Exactly? To
Somehow, where in one step you solve that.
Yes.
You know that it's a gap. And then you plug the solution into the Tillich-Neumann operator,
Yes.
and then okay. So you have an iteration that alternative.
Yes, you can do also this, for example, yeah.
Maybe since I expect to get some loss of it, then we'll be able to go to Nash-Moser type schemes.
No, for this to study the phenomenon operator itself, no, there's not. So you can control the loss of the real.
So it's fine.
Yes, and one. So let me do this. Let me compute the phenomenon operator for you at the free solvents.
So the equation from psi of the explicit form I think that is there, and then
From the Bernoulli equation, you take the Bernoulli equation.
so psi is boundary.
Exactly.
Where is the pressure? So where does the pressure go?
You've got my yeah. So in principle, you are right. You should have also the boundary, the pressure, the atmospheric pressure here. But the equation for psi actually, so now I will delete, but the equation for psi, so the psi evolves just in the homogeneous space. So this vector field is the potential. So just what matters. So it doesn't matter any constant value. So psi evolves just in the homogeneous space. And this is a vector field which preserves the homogeneous space in psi. And so in principle, you delete it will appear reappear realistically in the computation that I will do tomorrow. But for the moment, let me do it. Okay, let me do another thing. Let me compute for you. Let us compute together the divisional operator at the free surface and see how we can explicitly done. So let me do this. This is an example set. So I will compute g of 0 applied to some. So what you need to do, okay, so the free surface is surface per surface. So the 0 flat, so this is the eta, in this case, eta Ex is equal to 0, so this is the perfect C. You know, the C where everything is flat, nothing is moving, and perfect for, I don't know, perfect for swimming, light waves, or there's nothing. Okay, so what is the divisional operator in this case? So G of 0 applied to psi, what is, I use the formula, this is the derivative of respect to y of phi, derivative respect to y of phi, evaluated at the free surface, so y equal to 0, minus, then I have eta x, eta is 0, so this is the only term. So how do you compute this? So what we need to solve is we need to solve Laplacian phi equal to 0, phi equal psi at y equal to 0, derivative respect to y of phi tends to 0, xy tends to minus infinity. And let me do another simplification. It is not needed, but it is better for our purposes. So in a moment, I will construct Stokes wave. Stokes wave are 2π periodic, so I will put also a periodicity boundary condition here. So everything is periodic in the x variable. So let me add this. And so I want to solve it. Okay. So
Eta to pi per
yes, eta is 0. Eta is 0. But I asked for psi. We look for phi, which is 2π periodic in x. It's not really. You can solve the problem. You can solve the problem also without this. But it won't. But if I add this, and also let me put also a periodic boundary condition on psi, because also psi will be 2π periodic. Okay, you want to solve this, so what do? Separation of variables. In X, you expand it to the series. So you look for phi x y equal the sum k equals z of phi k y equal the r k x. And then what happens when you solve the Laplacian to 0 in this course, so in this variable. So Laplacian phi equal to 0, Laplacian phi equal to 0. This becomes minus k square g at k y plus second derivative with respect to y of phi at k y equal to 0. And this clearly has a solution p at k y equal to some coefficient. So this is a linear combination of exponential function plus beta k e to the minus ky. And then you need to impose boundary condition. Okay, so this is the solution of this. Then you need to impose the boundary conditions, and you have to find. Okay, so you impose boundary condition, and the first thing is you impose the boundary condition on the bottom, and on the bottom, remember the boundary condition is that the limit when y tends to minus infinity of the derivative with respect to y of p at k must be equal to 0. And so you see there is the difference. You see that what you see. So if k is greater than 0, when y goes to minus infinity, you need this coefficient to be 0. And when k is smaller than 0, you need this coefficient to be 0. And then, okay, and then you need to impose also the Dirichlet boundary condition. That means that psi at 0 must be equal to psi of x. And so phi at k y, what is this? So when k is larger than 0, this is so the Fourier coefficient must be exactly the same of psi. And so in the first case, k greater than 0, the second is 0. So here you get the psi at k if the ky, and if k is smaller than 0, you get the phi at k e to the minus ky, and we are almost done because now we have the formula for psi. So psi is the sum over the k positive of the psi at k e to the ky e to the I kx plus the sum k negative psi at k e to the minus ky e to the I x. And now to compute the Dirichlet operator, what I need to do, I need to take the derivative with respect to y and evaluate that y equal to 0. And so when you take the derivative with respect to y of the first term, you get the k going down when k is positive. When you take the derivative of the second term, you get minus k going down. And you evaluate at y equal to 0, meaning the exponential function disappears. And at the very end, what you get that this operator is when k is positive, you get k psi at k e to the I to the x. When k is negative, you get minus k. So you put all together, you get this, which is modulus of d. If we multipliers, the modulus of d psi. And so this is the way in which you prove the first expansion of the Dirichlet operator. When eta is equal to 0, the Dirichlet operator is the Fourier multiplier modulus of d. And this is also necessary. It is a non-local operator. Great. So now what I want to do is to go for traveling wave solutions of the water wave equation. Traveling wave solution. Okay, what does it mean? It means that I have this equation, and now we look for Stokes wave, meaning we look for solution of the system which have the form of waves traveling with constant speed. So a fixed profile, let me call it theta check, traveling at constant speed. With theta check and c check, two periodic functions. Okay, so the question is if the water waves equation possess solution having this form. And now we construct them. So this was first done by, at least formally, by Stokes, 1847. And nowadays, this is you will see, it's a standard application of Granda-Rabinovich theorem. So I will do this.
That's the way of house folks, because
Normally,
you can wear not about phone. The paper of clear, if I have not off, wasn't about it. So they They did the trigonometric expansion the same.
Yeah, but the thing you can solve it also without make it solve for stocks.
No, sure.
You also solve
No,
it.
I can mention that.
When you plug it in and you do this, you did this iterative scheme. When you plug it in, you solve it, you go on to the action. You go do the first two or three terms in the expansion of the Stokes wave. But
Computing the remainder step expansion was fun.
yes. Yes. No, you can go more or less by hand once you know how to invert the linearized operator, but Stokes.
No, but I was curious, but he's the age of it. And he goes, clearly, your solution was not automatic.
But not in these mathematical terms, but
It's more or less contemporary around the paper integration of even later.
yeah. Nice. Okay, so I take the traveling wave solutions, I plug them in the equation. So dt becomes for this become c dx theta check equal g of theta check c check, and then c dx of check equal to minus g theta check minus theta x check squared divided by 2 plus 1/2 g theta check c check plus theta check x c x check squared divided by 1 plus theta x check squared. Okay, meaning that I want to look for zeros, so the problem is equivalent to look for zeros of the following functional: if c theta psi equal minus c theta x plus g of theta psi and c cx plus g theta minus cx squared over 2 plus 1/2 g of theta psi plus theta x psi x squared divided by 1 plus theta x squared. And you look at this and you recognize that this is a bifurcation problem. This is a bifurcation problem because f, so this is a problem with depending on the parameter, which is c, the speed of the wave, and if you evaluate f at c, 0, 0, well, this is 0 for any values of c. This is the classical situation, so this is the classical bifurcation problem. So you have functions depending analytically on the parameter, and you know that for any value of the parameter, you have a trivial solution. And then, so this is the picture that you need to have in mind. The picture that you have in mind, so the space. This is the space of the parameter. This is your Banach space. You want to find the non-trivial zeros of this functional, and you know that you have a line of trivial solutions. So for any value of the parameter, you have a trivial solutions. And then what you want to do is to find some bifurcation value of the parameter, so some critical value of the parameter, at which point you branch off this axis and you construct non-trivial solution of the problem. And then
Horizontal axis.
it's not
This the horizontal axis, it's the parameter axis.
yes, this is C, and here you have the Banach space where you want to solve it. So for any value of the parameter, 0 is the solution, trivial solution, and then you want to find some critical values of the parameter at the point in which point you branch off
This is classically
the axis.
the Jacobian of the path. Well, you need this like Jacobian.
It is a necessary condition. And so this speed of the Stokes wave is exactly the speed at which the differential with respect to this variable of the functional is not inverted. Okay. And in this case, it will have a kernel. The invertibility is broken. The invertibility is broken because we have a kernel, a non-trivial kernel. And this is the setup of the Kran-Darabinowitz theorem, which I was now telling, but not proof.
But there is no finite dimensional assumption that somehow the dimension of the kernel is finite dimensional.
Not only finite dimensional, but for Kran-Darabinowitz, one dimensional.
So this is because you want just one hypothetical edge.
Yes.
Because you would have a map. It's always stuff.
I mean, what you do in the information problem is this. So usually what you do is you try to do a Lyapunov Smith decomposition. And then you reduce the equation to the kernel equation. Now,
In this case,
you can find dimensional. And so you are. You have a finite dimensional problem, and then you can use whatever method you want to find the solution to a finite dimensional problem. You have many strategies, so there are many strategies. So the easiest one is Kran-Darabinowitz with one dimensional, but you can have also
but
you can
the
have
key issue
additional
that
method,
you can
you
apply
have theory.
but the key issue that you can apply Kran-Darabinowitz that
Yes. The principle
so in this problem,
in this problem it will be one. In this problem I will reduce, I will add an assumption,
okay.
such a, but
No, because I don't
so I will make a smart observation in such a way that the kernel will be one. In principle, it's two. And then I will reduce to one with a smart observation.
because in my mind there was not one.
It's two, but you make a smart observation and it becomes one.
Wait,
But it's very easy, the smart observation. Symmetries. Use the
If it's
symmetry.
easy, it's not smart.
No, I mean,
It's smart.
it is smart.
It's not easy.
It is easy, but it's fun. Okay, so Kran-Darabinowitz, let me state Kran-Darabinowitz. Do you know Kran-Darabinowitz? Bifurcation theorem or not? Never seen, so let me state it.
It's spectacular.
Right, yeah. Kran-Darabinowitz. Kran-Darabinowitz, so take a function f, which is analytic, from R times U with values in Y. U is an open set in a Banach space X containing 0. And what we know is that f of C0 is equal to 0 for any value of C. And moreover, you have these three assumptions. So the first one, so as we mentioned, so the kernel of the differential of U of f at this point, so there exists a C star such that the kernel of this object is one dimensional and it is spanned by an element U star, so this is one dimensional. And this is really necessary, no? Because if you are at the point in which the differential with respect to U of f is invertible, implicit function theorem, there exists a unique solution, but you have already a solution, which is the trivial one, so you have only the trivial solution. So to construct something non-trivial, you need the linearized operator at the Stokes, the linearized operator at this point to be non-invertible. And we ask that there is a kernel one-dimensional. Second condition, you also need that the image of the differential respect to U of f at C star 0 to be closed and with codimension 1. And with codimension 1, meaning the dimension of y over the image is equal to 1. And 3, you need the transversality condition, meaning that you compute differential respect to U of f at C star 0, you take also the derivative with respect to C of this object at C star 0, and you evaluate the derivative with respect to C of the differential with respect to U of F at C star 0, and you evaluate at the element of the kernel. So this must not belong to the range. And then the result is that you want to cancel here. Let me go here. Then the theorem says that C star 0 is a bifurcation point. And in particular, there exists epsilon 0 greater than 0 and a local bifurcation curve parameterized by epsilon. So this is the curve C epsilon, U epsilon, which belongs to R times X of class analytic. And moreover, C epsilon is the bifurcation speed plus a correction for the epsilon, and U epsilon is epsilon U star. U star is the element in the kernel plus a correction for the epsilon square. And if you want, you can further compute this. So Rabinowitz tells you that that in this case, under this assumption, there is a bifurcation curve bifurcating from the critical value C star, and the bifurcation looks like a curve, something like this. And the reason is that in principle you might have bifurcation looking different. Then you might have also bifurcation with multi branches, but not in this case, not in Rabinowitz. Rabinowitz excludes this situation and tells you it excludes this situation, and it tells you that the bifurcation happens as a curve.
And it's only one of the C star branch that
No, there are many. For the problem, there are many. But once you have a value before now we will see the bifurcation values. Okay.
Forse by analyticity, you could extend the expansion of C epsilon and person.
Yes.
Because you are not forced to write the points of some square. They give you enough for what you want to do.
So it is enough for the figure 8. It is enough to expand at order 2. But to describe the isolas, you need all the expansions. And so we have a social class for all the expansions.
So this statement is not enough.
Is enough? No, it's not enough. It's not enough.
Because you need the reality terms.
For the epsilon squared for the figure 8, and more term for the isolas. You need to arrive at order P for the isola, but since P is arbitrary, you will get it. Okay, so but let me try to apply then Rabinowitz to our problem. So what we need to do is to find the critical value. So we need to compute the differential with respect to eta and psi of f at the value C star 0, 0, and find the kernel of this operator. So let me make now also a the smart observation. The smart observation is this. The smart observation is this. So if eta is even and psi is odd, then this is an exercise for you. The Dirichlet-Neumann operator is an odd function. Exercise for you. Not difficult. You will just improve. Do it by considering the elliptic problem. Exercise for you. What does it mean? Well, it means that if you take the nonlinearity f, which it is I. Let me write f again. F c theta psi was equal to minus c theta x plus g of theta psi c psi x plus g of theta plus cx squared over 2 minus 1/2 theta psi plus theta x cx squared over 1 plus theta x squared. What does it mean this? It means that if we evaluate this at the function theta which is even and at the function psi which is odd, this is odd. This is the exercise which tells you that this is odd. So this is odd. Psi is odd. This is even, and this again is even. And this means that we have the symmetries, and this is the symmetry that will reduce the dimension of the curve from 2 to 1. So this means the first component is odd, and the second component is even, and then the second factor, which instead I want.
There's some say physical interpretation of this.
Invariance by translation.
Okay, so that's yeah.
Yeah, invariant by translation. The equation. And so, yeah, you can always translate.
Yeah.
Excellent. And then the second factor is that actually the function f, the linear function, is an analytic function from R times HS even of the torus times HS of the torus into the function. So the first component, remember you lose one derivative, the Dirichlet-Neumann always lose one derivative, and it is analytic. So in HS minus 1 odd of the torus, HS minus 1 even of the torus is analytic. And this is not so. Sorry, I cannot do it in the 10 minutes that I left, but so there are many proof of this. So, for example, for the situation which applies to the figure 8, or for the exact statement that we need in the theorem that I will start proving tomorrow, I refer you to a paper that I proved with Massimiliano Berti and Paolo Ventura. I think it's on Ravelli Conti of the Licei. And it is about the analyticity of this operator. I mean, I don't think there is nothing really new, but we needed to somehow redo the argument in order to prove that the function f is analytic also as when you replace HS to a space of analytic functions, which was needed make the expansion. At least here you have sample the proof, which I think is important. Okay, fantastic. And so, we apply Kandel-Rabinowitz. Okay, let's apply Kandel-Rabinowitz. What do we need? We need to find here the kernel. We need to find the kernel. We need to find the kernel, and so in order to find the kernel, the first things I need to do is to compute the differential with respect to eta psi of f at c 0, 0 in direction eta check c check. What is this operator? Okay, I need to take the derivative of this. Okay, the first term is easy, minus c eta check x. Then we need to compute the differential, the derivative of this. We need to compute the differential of this object. So the differential with respect to psi of this object. So let me compute the differential of this object. So the differential with respect to eta psi, differential with respect to eta psi of the Dirichlet-Neumann operator in the direction eta check, c check, what is? So once I take the derivative with respect to the second variable, this is easy because the operator is linear. So this is just g eta applied to the variation, plus, then I need to take the derivative with respect to the internal variables. So this is difficult, g prime is difficult operator, g prime of eta, evaluated in direction eta check, apply to psi, but we need only the linearization at 0. So I want to evaluate this at eta psi equal to 0. So the first term is G0 psi check. G0 we compute it, the Fourier multiplier modulus of B. So this is modulus of B psi hat. And instead here I don't know what it is, but evaluate at psi equal to 0. This is linear in psi, so this is 0. And so this is the object. And so here we get plus modulus of D psi hat. And in the second line, what I have, so this is linear, so this, I have G Cx at plus G eta at. And then this is a quadratic term, this is also a quadratic term. When you linearize and evaluate at 0, you get 0. So this is your object. Okay, so let's okay. So now let us expand eta. So eta is an even function. I expand it in the cosine. Eta is the sum of eta k cosine of kx. Psi I expand it's odd, so I expand it on the sine basis. And so this operator, the differential with respect to eta psi of f c 0, 0 in direction eta check becomes, use this computation, that easy, becomes the operator. So in Fourier components, when you expand, you get sum over here equal to 0, and here a also back to 0. So this is the operator. I write it like this. So the term C N G C N applied to theta N C N. This is so let me write it in Fourier function. Theta N cosine of N cosine X sinus of and not that right so the right operator is the nth component of the right operator. So properly, so this becomes So this becomes the sum of Cn theta n plus n psi n sinus of nx and Cn times Cn plus g theta n cosinus of ns plus you have the zero component which is 0 e theta zero. Okay, and so you need to find the kernel. And so what does it mean for this operator to be invertible? It means that for n g and f, so g which is in h s minus 1 bottom, and f which is in h s minus 1 even, so we are able to solve, we are able to invert t 0 eta at psi at equal to g f, and so you write it in Fourier. And so you write it in Fourier, and you expand the g and f here as well. And so this is invertible if and only if. So the operator is invertible if and only if for any n greater equal to 1. So with zero component you can always invert, and instead for the other you need to be able to solve the system Cn and G Cn applied to theta n Cn equal Gn Cn. So only if and only if for any n it's solvable. But we don't want it to be invertible. We want it to have a kernel of dimension 1, meaning that we want one and only one of these matrices to be not invertible, so to have a kernel. Okay, we need one and only one of this matrix, so let me call this MC of n of MC of n to have a kernel. Okay, so if all of them are invertible, you invert the operator. We don't want to invert the operator, we want the kernel of the operator, meaning that we want at least one of these matrices to have a kernel, and we want the kernel of dimension 1, meaning exactly one of these matrices must have a kernel. What does it mean for this matrix to have a kernel? It means that the determinant must be 0. The determinant of this must be 0. And what is the determinant? It is c squared n squared minus ng. This must be 0. And so this means that c must be equal, solve it, to plus or minus square root of g over n. So if a value, okay, if c is equal to one of this value, you have a kernel. And of course you have two choices which correspond to the two speed of propagation of the traveling wave, so one on the right and the other one on the left. And then we want on one kernel, meaning, so you fix n, for example, let's fix n equal to 1, and then this gives a c star, a critical speed of, and let's also fix a sign plus, so square root of g. But then you want that for this value, all the other matrices have a determinant different from 0. But this is true because this function is injected. Okay. So okay. So what you want is that m of c star of n, so the determinant of this function is different from 0 for n different from and different from 1, and this means that what is the determinant, when determinant order. This means exactly that for all other values, you want the square root of g over n to be different from the square root of g, and this is of course true because this function with special relations. Okay. Okay, so this is the condition that the determinant is equal to 1, that the kernel is one dimensional, and then I think I need to stop. Now, I finish 1 minute to finish. So then we check the condition on the image, and then let me check the transversality condition. So for the transversality condition, no, it's a bit more. Then the exercise. So since I don't have time, this becomes an exercise. The exercise for you is then to check then exercise. You can also compute the image exercise. Check then the range of the operator is indeed the orthogonal to this function, to C star sine of x and minus cosine of x is the L2 orthogonal to this vector. And you get it by understanding what is the other object in the range of this matrix. And so the final condition is the transversality condition. Let me check the transversality condition. So what you need to do is compute the derivative with respect to C of the differential with respect to eta m psi of f at the point C star 0, 0 in the direction of the kernel, eta star C star, and this shouldn't stay in the range. And also from this computation, we get the kernel, and the kernel, the element of the kernel, check it, eta star m C star, this is equal to C star cosine of x and minus g sine of x. This is the element of the kernel that you get imposing the determinant here equal to 0. This belongs to the kernel. And so the transversality condition, how does it look like? So I again deleted the equation of the start, but it doesn't matter because this is the eigenvector. This is the eigenvector. So it's the kernel of the eigenvector which corresponds to this. When you solve this, you get
With n = 1.
Sure, with n equal 1. But you can choose whatever n you want here, and you will have the speed associated to that. And how does it look, this operator? DC. Okay, but this is quite easy to compute, no? Because we need to take the derivative with respect to C, and C enter just in the transport term, in the transport part of the equation. So you remember the part of C eta x at C, C at x. So you need, when you take the derivative of this, and this is what you get, compute this, but actually, as I wrote it, there was a minus here, minus eta x, evaluate, and I need to evaluate this at the kernel, eta star, C star, so this is minus eta x star, Cx star, and then what you need to compute, you need to compute this, so minus eta x star, this, so this is C star, derivative of the cosinus is minus sinus, and the derivative of the sinus is the cosinus, so I get minus, but I have a minus here, so it becomes plus, and it becomes minus g cosinus of x. And then what you need to check is that if this belongs Here there is also a G, sorry. Here there is a G, the speed, and we need to check if this belongs, this doesn't belong to R, and it does. And it doesn't belong to R because R is the orthogonal vector. And here we get the section. Okay. Okay, so you can fill the details and verify that you can apply Krandara-Rabinovitz. And so at the very end, what you find in the theorem and what you find is that if you take S sufficiently large and the minimal regularity is 5/2, there exists epsilon 0 greater than 0 and the function C epsilon and beta epsilon C epsilon, solving such that beta epsilon x plus C epsilon t and C epsilon x plus C epsilon t solve the waves. And moreover, from Krandara-Rabinovitz, you know that C epsilon is a perturbation of the critical value, C star, and our C star was square root of G. And instead, it epsilon is a perturbation of the function in the kernel. So it's the square root of G, epsilon square root of G cosine of x plus some other correction, and which you can compute. And but we don't comment psi epsilon is equal to instead minus G minus G epsilon sinus of x plus top of epsilon square. And so you see exactly that at first order the Stokes wave looks exactly it is a cosine, and then you have a your correction. Exactly.
So here that taking one.
Yes. Yes. And you can construct, you can bifurcate from NN with the critical speed, which is the square root of G over N. And at each of these points you can construct. Okay, so I was a bit fast in the final part, but if you want the details, there are some lecture notes, for example, on my website, in which I have all the details for this. So you can check the details there. Thank you. The 5/2 is the minimal regularity that you need for the division normal to be analytic. Should be 5/2. I mean, if you work, you optimize.